Alright, so let's continue with our review. We are in the middle of Skill 3, Relations and Functions, and here they're asking us to find the domain of these new functions, f plus g, f minus g. Now, although in the previous problem we found algebraic expressions for f plus g and f minus g, we really don't need to find algebraic expressions. What we need to do is find the domains of the individual functions that built this new function and intersect their domains. So let's take a look at this function f. I'll put a little f down here below the d just to remind myself that that's the domain for this function f. Well, the domain is the set of all real numbers, excluding any values that cause me to take the square root of a negative number. I don't have any square roots. It's the set of all real numbers excluding any values that cause me to take the logarithm of 0 or a negative number. Well, I don't have any logarithms, but I do have a variable in my denominator, so the only worry I have is about division by 0. Since 4 minus 4 is 0, that's what I exclude from the domain. So the domain for f is the set of all real numbers. So here's my number line, excluding the number 4. Everything else is okay. None of these other numbers on the number line cause division by 0. So my domain is a set of all real numbers excluding 4. So the domain of f, it's split into two regions. On the left, it's from negative infinity up to 4 and not including 4, or you're to the right of 4, which is from 4 to positive infinity. Alright. Now let's do the same thing for the domain of g. Well, you can see how similar it is to the previous problem. I'm not worried about the numerator and stuff. I can have any value I want in the numerator. I am concerned about division by 0. So this time, the domain for g is a set of all real numbers excluding the number 2. Let's do this in a different color. So if we excluded 4, you can see how similar it's going to be. You can draw a number line if you need to, but this guy is going to be from negative infinity up to 2, not including 2, or bigger than 2, from 2 to infinity. Okay. Now, you'll notice down here that I have a and b on the same slide here. Well, that's because if I'm going to build a new function through addition or subtraction, these new functions are going to have the same domain. So I just went ahead and put them, as soon as I find the domain for a, that's also going to be the domain for b. Now, it doesn't ask me what the domain of f times g is, but if I were multiplying these two functions together, I'm going to get the same domain. The only time I'm going to get a possibly different domain is with division or function composition. Alright, so the domain of these guys, well, you have to be in the domain of f and in the domain of g. Our domain of f plus g is all real numbers excluding 2 and excluding 4. So let's draw a picture of that just to help us out. Here's a number line. In order to even have an output to add to it for f, we have to exclude the number 4. So here, if I draw a circle around 4, and to even have an output for g, we have to exclude the number 2. So any other number, you'll have an output that you can add together from f and an output from g. So the domain is a set of all real numbers excluding these two values. And this is going to also be my answer for b. So I have three regions to describe. On the left, it's from negative infinity to 2, because we always go a smaller number comma a larger number when we're writing the interval. Or you're in the interval from 2 to 4, or you're strictly bigger than 4 from 4, and since the arrow shaded 4 to infinity. So there's our final answer for both A and B. All right. Here, it's still the same problem, still the same function, but in part C, they're asking me to find the domain of this new function for division. So I'm going to steal my previous answers for the domain of f and g. I've already done that work. All right. Now, remember that f and g, I'm concerned about division by 0. So I know that this, most of the time, we can figure it out without writing it out. But here, maybe it would be a little bit helpful to write it out. The numerator is f of x, which is 3 over x minus 4. So you're not going to have a value to put in the numerator if you allow x to be 4. In the denominator, we're worried about 2, but this numerator right here itself is in a denominator of this whole thing. If we were allowed x to be 0, what would happen? If you were to evaluate this division at x equals 0, everywhere we see 0, everywhere we see x, we would replace it with 0. So our numerator would be 3 divided by negative 4. And our denominator would be 0 divided by negative 2. All right, 0 divided by negative 2 is 0. In the numerator here, why, we can just keep this as negative 3/4. So if you want to convert it to a decimal, hey, that's fine. But down here in this denominator, if that's 0, if you go to put that in a calculator, the negative 0.75 divided by 0, that's undefined. We can't allow this numerator to be 0 because itself, it's in a denominator. So we have to add that restriction. We had the previous two restrictions that x can't be 2 and x can't be 4. So let's put that on a number line. Here's, say this is 2 and to the right of that is 4. But we also just saw that when x is 0, you have a 0 in this denominator. So we have to exclude the number 0. So everything else is okay. So our domain is a set of all real numbers, excluding 0, excluding positive 2, and excluding positive 4. So we need to describe that set, and we can use interval notation to describe it. All right, so our domain for this f divided by g is the set of all real numbers on the left here from negative infinity to 0, or if you're between 0 and 2, or if you're between 2 and 4. Because see, when we see the union symbol, we can translate it into English as the word or. So you're in this interval, or you're over in this interval. And since the arrow shaded, it's going 4 to infinity. So there's our final answer. It's not the same as the A and B were. Sometimes it will be, but when your denominator, when this g of x, when this denominator is itself a fraction, you have to be concerned with that numerator. And we had a variable in the numerator. All right. Now here, this function composition, remember that we can think of this function composition as like an assembly line. And you start with the second one. So we're going to take input from our domain, and it's going to go into G. And then the output of G, it goes into, is the domain for F. And the output of F here. Well, for us to get to this final, and we can write this as f of g of x. To get this final output, you have to go through this function and also through this function. So it has to be well defined to go through each function. You won't be able to get an output for g if you allow x to be 2. So right off the beginning here, we can't let x be 2, so we're going to throw 2 out of the domain. So I'm going to write it like that for right now, that x cannot be 2. Now, the input into f, this input into f cannot be 4, because 4 minus 4 is 0. But remember, the input into f is the output of g. So this g of x, that's how we use the notation to write the output of g. This g of x cannot be, it can't be, if we look at f, it can't be 4. Okay. But see, this, we're not saying that x can't be 4. We're saying that g of x can't be. We've got to figure out what x, if you put into g, causes an output of 4, and then don't put in that x value. So if g of x on the left-hand side is this x over x minus 2. And I'm going to temporarily let it equal 4 so I can figure out what value of x to avoid. I'm going to write 4 as 4 over 1, and I have a proportion here, a fraction equal to a fraction. And one technique to solve proportions is to cross multiply. So along one diagonal, I get x. X times 1 is just x. And along the other diagonal, 4 times x minus 2 is 4x minus 8. So if I add 8 to both sides and subtract x, I get that 3x is equal to 8. Or, boy, I'm running out of room, so let's move everything up. Divide both sides by 3. If x is allowed to be 8/3, then when you input it into g, the output of g will be 4. Well, if you put 4 into f, it causes division by 0. So to avoid the 4, to avoid the division by 0, we have to avoid letting x be 8 over 3 over here in my domain. So those are the only two values that we have to throw out. 8 over 3 is bigger than 2. 3 goes into 8 twice with a remainder of 2, so 2 2/3. All right. I'm just going to leave it as 8/3 when I write it out, though. So I've got this number line, and I'm going to exclude the number 2, and I'm also excluding the number 8/3, 8 divided by 3. Now, not because it causes a problem through g, but if you put in an 8/3 here, you'll see a problem on down the assembly line over here with this function f, because 8/3 here will cause this output to be a 4, and 4 into f will cause an output that's undefined. We can't have that. So, hey, that's thick. The set of all real numbers excluding this. Well, how do we describe this interval? The domain of this function composition, f composed with g. Since this left arrow is shaded, I'm at negative infinity. And I always have an open parenthesis at negative infinity because that's not an endpoint. That arrow is not a number, and I can't include it. Now this 2 is an endpoint. I don't want to include it, so it's an open parenthesis. Sometimes you will include endpoints, and there'll be a solid dot, and you would have a bracket there. Or you're in this interval, or you're in between this 2 and 8/3. Or you're bigger than 8/3. That's going all the way to that arrow, which is positive infinity. So here is our final answer for the domain of this function composition. Here it's asking us to find the inverse. This notation is just inverse notation. Again, f does not mean f times x here. This superscript of -1 is not an exponent. All right, so it's notation. So you have to understand the context. You know, we ignore the function notation and we write it using x and y. So if we write our equation, y equals 4x minus 3. Well, when you're finding the inverse of a function, you switch the domain and range. Well, the domain is a set of x's and the range is a set of y's. So if I'm switching the domain and range, in this equation, I have to switch these variables. So everywhere I see a y, I rename it as x. And where I see an x, I rename it as y. Now I need this equation to be written in terms of y. I need to solve for this y. So I need to add 3 to both sides. I'm going to write the 4y on the left, x plus 3, and now I'm going to divide by 4 to get this y by itself. Alright, now you're not going to see the answer of our multiple choice written like this. It's going to use this inverse notation. It's going to be written f inverse of x is equal to x plus 3 over 4. Now, it's not impossible that they would take this single fraction and split it into 2 fractions. You're dividing both of these terms by 4. So this x, it gets divided by 4. And this 3, it gets divided by 4. And to divide by 4 is the same as to multiply by 1/4. So you might even see this first term written as 1/4 times x plus 3/4. So since this equation is a line, this is in slope-intercept form, where the slope is 1/4 and the y-intercept is 3/4. So here the original function was a line, and the inverse is also a line. Like I say, you're looking for this as an answer among the choices, or it could be written like that, or it could be written like this. So be aware of how to algebraically manipulate your answers. If you have the right answer, you want to be able to recognize it. So we have the same directions here. It's just this function is a little more complicated. To find the inverse, we're going to use x and y notation. So instead of f of x, we're going to write y. And now we know that to find the inverse, you switch the domain and range, which means in our equation, we're going to switch x and y. So I'm going to make this a proportion, and I'm going to cross multiply. Along this diagonal, I have x times the quantity y plus 5. And along the other diagonal, I have 1 times 3. Well, remember, I'm trying to get the y by itself, but before I can do that, I need to get that factor y plus 5 divided by itself. So I'm going to divide both sides of this equation by x. X divided by x is 1, so on the left I have y plus 5, and on the right I have this fraction, 3 divided by x. Now, to get the y by itself, the inverse of adding 5 is to subtract 5. So if we subtract 5 from both sides, that'll cancel. We have y is equal to 3 over x minus 5. Now, it's not going to be written like that. They're going to use this inverse notation and write it as 3 over x minus 5. Now, it's possible that they could combine these two. They could write this 5 as a fraction, 5 over 1, get a common denominator, and add those together. So what if we look at our choices and we don't see this as a possible answer? Let's come over and say that that might be rewritten. Here I need a denominator of x, so I'm going to take this 5 and multiply it by the number 1, but I'm going to write the number 1 as x divided by x. What does that get me? Well, it gets me a common denominator. I've got 3 over x minus, if I multiply these numerators, I've got 5 times x, and 1 times x is just x. So we've got 3 minus 5x over x. So that could be how it's written. And of course, they would use this inverse notation. Or maybe they write the negative 5 first and then the 3. You know, it's possible that they could write it negative 5x plus 3 over 3. So once we get this final answer of 3 over x minus 5, we have to recognize that in a multiple choice test, they might rewrite this as this. They look different, but they're the same equation. They mean the same thing. Or it could be written like this. All three of these look different, but they're all equivalent to each other. All right, so if you ever take a calculus class in your future, this is referred to as the difference quotient, and you'll study it when you study a thing called the derivative. All right. Now, people have made this so much more complicated than it needs to be. This is a fraction. I've got g of x plus h, and then we're subtracting from it the original function g of x. Well, they've given me that function right there. And this whole thing is just being divided by h. So what I need to do is figure out what to replace this g evaluated at x plus h. So let's come down and do some scratch work. This function g, what does it do to the input? Well, this function g, no matter what the input is, no matter how simple or how complicated it is, g always creates a subtraction problem. The first number is 5 times the input. And the input is always found between these parentheses. So like I say, if it's an easy number or a simple expression, it goes there. If it's complicated, it goes there. This and this are identical. And the second, in the subtraction, the second number is always 3. Well, we're trying to evaluate this for an input of x plus h. So we write x plus h here. So now this expression, well, let's just distribute this. And 5 times x is 5x plus 5 times h is 5h minus 3. Everywhere I see this g evaluated at x plus h, I know it's the same thing as 5x plus 5h minus 3. So let's come up here and replace that. I'm not going to write this g evaluated x plus h. Down here in my scratch work, I have shown that this can be written as that they are equivalent, they look different, but they are the same thing. Now, we're subtracting from this function. Well, here it is up here. G of x, there's g of x, is equivalent to 5x minus 3. I have to be careful because I'm subtracting not just the 5x, I'm subtracting the whole thing. All of this is being divided by h. So if I can simplify this expression, this fraction, I'll have my final answer. Alright, I'm going to get rid of my scratch work down here. I'm done with it. You could, if you need to still see it, you can pause the video and go back. Alright, I'm going to stop writing in different colors and just finish this in black. I've got the 5x plus 5h minus 3 minus the first term 5x, and when you subtract a negative 3, we just write it as 3. Now, also a nice observation when we did these problems, you'll recognize that every term that does not have an h will end up getting canceled. This 5x doesn't have an h. Somewhere I know there's going to be a negative 5x. I've got a positive 5x, and there it is, a negative 5x. They add up to 0. Now this has an h. I know it's not going to cancel. This negative 3, I know it doesn't have an h. I know somewhere there's going to be a positive 3. So hey, that means my numerator is 5 times h divided by h. Now these are factors. If it was 5 plus h, I wouldn't be able to cancel this, but being factors, you can cancel common factors. The h divided by h is 1, and 5 times 1 is 5. So this thing that they refer to as the difference quotient, this g of evaluated at x plus h minus g of x all divided by h, simplifies to just the number 5. Well, hey, I have another observation to point out. This 5, if you look here, you see that 5? This was a line, and this 5 is the slope of the line. This different quotient, if it's a line, it'll always equal your slope. So if you're running out of time and you see that g of x is equal to, I don't know, 1/2 x plus 1, I know that I'm going to look for a difference quotient that if you take the time to do all that stuff we just did, it's going to reduce and it's going to equal 1/2. Now, that's not going to be the case if this is a quadratic. You can't use that trick. But if it has an x in it, if it's a line, it's going to be the slope. All right. So I hope that helps, because that could be a huge time saver and a nice check. If you go ahead and do the work, I knew before I started the problem that I was going to get 5, but then I have experience. All right. Now, is that it for the? That's it. So I'll continue skill 4 on a separate video. So I hope this helps.